Good morning, Applied Physics students. Here are your Chapter 4, Section 6, 7, 8, and 9 notes. You got the Section 5 one all by itself because it was a longer section and I didn't want to give you a ridiculously long set of notes to take. So, we talked about how fast in Section 5. Today we're going to talk about in free fall how far something moves. So we're going to be talking about distance. Okay. So kind of the first thing to know here is that how fast, which remember we're talking about speed or velocity, and we really can kind of use those interchangeably, because the only difference between them is speed is scalar and doesn't have a direction, and velocity is vector and does have a direction. And how far, which we're talking about distance, are not the same thing, which I think you know. But again, we just kind of want to reiterate that these are going to be different things. So, I want to take a look at table 4.2 and 4.3 kind of together. So, I'm not going to use an image from your book. I'm going to kind of create my own. And I think I'm going to do that on a new sheet here. Okay? So, the things that I want to kind of look at here are, I still want to look at elapsed time. Which is still going to be measured in seconds. And that's our t. I want to look at instantaneous speed. Which is still going to be measured in meters per second. And that's, our symbol is the little v. I want to look at average speed. So, and that's also going to be in meters per second. And that doesn't necessarily have a symbol. I want to look at our distance fallen. Which is going to be measured in meters. And that's a d. And then I kind of want to look at our total distance. Just worried about that. So I sort of would really like you to make this chart. All right, and for the elapsed time, we're just going to go 0, 1, 2, 3, 4. And then we'll just kind of say t, okay? So, instantaneous speed. Remember, we're talking about the acceleration due to gravity, okay? So, we're going to pick up 10 meters per second every second we fall. So our instantaneous speed at time 0 is going to still be 0 meters per second. But in the first second, I'm going to increase my speed by 10 meters per second. So my speed will be 10 meters per second. In my second of fall, I'm going to increase by another 10 meters per second. So I'm now going to be going 20 meters per second. I'm going to pick up another 10 meters per second, so that means I'm going 30 meters per second. And I'm going to pick up another 10 meters per second, so I'm going to be going 40 meters per second. And kind of just to keep these all I can make them velocities by just saying that they're all going downward. Now, what we should hopefully kind of notice is our instantaneous speed here is that v equals our acceleration due to gravity times t. And remember, our acceleration due to gravity, g, equals 10 meters per second squared. Okay? So, we've looked at our instantaneous speed. Next, we're going to look at our average speed. Now, to figure out our average, remember we're going to take our first velocity and our second velocity and divide it by 2. Just like we do averages in math class. So, 0 and 10, okay? 10 plus 0 is 10, divided by 2 is 5. And I'm not going to go ahead and put units on there because I have my units up at the top. And this is my first second. So now I have, for my second of fall, 10 plus 20 is 30, divided by 2 is 15. For my third second of fall, 20 plus 30 is 50, divided by 2 is 25. And for my fourth second of fall, 30 plus 40 is 70, divided by 2 is 35. So again, remember, these are my speeds. I can make them velocities by saying that I'm falling downwards. So this is my average speed. Next, we want to look at how far we've fallen, right? This, what we've talked about so far, we had talked about on Friday and previously when we did these calculations and looked at this speed and average speed, when we were looking at how fast. But today we're talking about how far. So today we have to start to talk about how far we've fallen. Now, again, it's easy, right? At time 0, we have fallen 0 distance. Okay? Now, here's how we're going to get this distance fallen. We're going to take, okay, our average speed and multiply it by the time. Because remember, distance equals speed times time. So my average speed during the first second of fall is 5 meters per second, and I do it for 1 second. So my distance that I've fallen is the 0 that I started with plus 5. Well, actually, we'll do it this way. Let's do it this way. My distance fallen is 5. So over here, I want to look at my kind of total distance. And my total distance, again, at the start is 0. Now I've fallen 0 plus 5, which gives me a total of 5. And my total distance here is also going to be, I see that I left my units out, is also going to be in meters. Okay? So now, time 2, in the second of fall, my average speed is 15 meters per second times the 1 second. So I'm going to fall 15 more meters. So my total distance is going to be the 5 plus 15, which equals 20. The 5 that I had fallen in the first second plus the 15 I've now fallen in the second gives me my total distance, right, that I have fallen so far is 20 meters. All right, I'm ready for my third second, right? 25 meters per second times 1 second means I fall 25 more meters. So, I had fallen 20. I fall 25 more, which gives me 45 meters total that I've dropped. So in 3 seconds, right, our kind of picture here would be we're like on a cliff, right? And here's my ball. The first time it's 5 meters down. The next time it's fallen 3 times as far. And the next time it's fallen even further. Okay? And my total distance right now from the edge of my cliff would be 45 meters. All right, my last one. My average speed is 35 meters per second for 1 second, so that means I fall 35 more meters down. So my total distance is the 45 I've already fallen plus 35 more. Right? So 45 and 35 gives me 80 meters total. Okay? So to figure out my total distance, okay, my distance I've fallen is going to be 1/2 GT squared. So to kind of check that, let's take time 3 seconds. So this would be, okay, so I'm just kind of checking this right now, right? 0.5 for 1/2 times 10 times 3 squared. So 3 squared is 9, times 10 is 90, divided by half is 45. And notice, right, I have 45. So this really, I probably should go ahead and be consistent with. Oops. I should write this in red because this is my total distance, is 1/2 GT squared. Now, we're going to see in a couple minutes, okay, and so I'm going to kind of add it to it here, that my acceleration due to gravity is constant, meaning it's not changing, it stays steady. And anytime I have a constant acceleration, I can also use AT here. And I can also use an A over here. Why is that important? Because if I'm talking about accelerating my car at a constant speed and I want to figure out how far I've gone, I can use this distance equation. If I'm talking about accelerating my car at a constant acceleration, I can figure out what my velocity is after a certain period of time by using this equation. So it doesn't just work for falling objects, it works for any time I have something happening in a constant or steady way. So this is that combination of table 4.2 and 4.3 together. So what we see here, okay, is that for each second of free fall, an object falls a greater distance than it did the previous second. Right? So what that's saying is, right, our distance of fall in our first second was only 5 meters. In the second second, we fell 15 meters. In the third second, 25. In the fourth, 35. Okay? You should kind of see a pattern here, right? So the next second, you would fall 45 meters. Okay, so that's all this is saying, is for each second of free fall, an object is going to fall a greater distance each time than it did the previous second. We have an equation that we can use to figure out this distance. Our distance is 1/2 our acceleration due to gravity times our time squared. And as I mentioned a couple minutes ago, for any constant or steady acceleration, you can use these equations that we have. So v, our velocity, our instantaneous velocity, is our acceleration times our time. And to figure out our distance is 1/2 our acceleration times our time squared. The only difference here is when we're in free fall, our acceleration is our acceleration due to gravity. Therefore, okay, we have those equations where it's v equals gt and d equals 1/2 gt squared. So I want you to realize those aren't separate equations. The only difference is we've kind of said when we're falling on Earth, the acceleration that acts on us is gravity, and so we put a g in instead of an a. So I want to take a look at some problems. How far will a freely falling object that is released from rest fall in 2 seconds? Right? So we want to know our distance. Okay, we want to know our distance. And our time is 2 seconds. So we're going to use that equation d equals 1/2 gt squared. So 0.5 times g, which is 10 meters per second squared, times our time, which is 2 seconds, squared. So 0.5 times 10 times 4, right? 2 squared is 4. 4 times 10 is 40, and half of 40 is 20 meters. And again, how do those units work? I have meters over second squared times second squared. So those are going to cross out, and I'm going to be left with meters. All right, what if we have the same question pretty much, but we want to talk about in 10 seconds how far it's going to have fallen? Right? So, again, we want to know our distance. Our time this time is the 10 seconds. Our equation is the 1/2 gt squared. So 1/2 10 meters per second squared times the 10 seconds squared, which is 1/2 10 times 1,000 or 100. 10 times 100 is 1,000, and half of 1,000 is 500. So 500 meters. Right? It's pretty fast. Something falls in 10 seconds, 500 meters. And the last one we want to do is the same question, but now we want to say the object is going to fall for just half a second. Again, you might need a calculator for this one. Okay. So again, we want to know how far, our distance. Our time this time is 0.5 seconds. So our equation is still the 1/2 gt squared, 1/2 10 meters per second squared times 0.5 seconds squared. Okay. And when you put that in your calculator, you should get 1.25 meters. So we're going to take a look at another kind of question here. This time we're going to consider a rock thrown downward with an initial velocity of 15 meters per second. What is the acceleration of the rock after 1 second? And this is kind of a trick question because this doesn't require any math. See if you figure it out without any math, right? We're on planet Earth. What's the only force that's going to be acting on this object to accelerate it? Gravity, right? What's the acceleration due to gravity? Therefore, it's 10 meters per second squared because the acceleration due to gravity is always 10 meters per second squared. So, want to take a look at the page 56 think question. The page 56 think question says an apple drops from a tree and hits the ground in 1 second. What is the speed upon striking the ground? What is its average speed during the 1 second? How high above the ground was the apple when it first dropped? So again, I kind of like a little picture, right? So I have a tree, I have an apple in my tree, and my apple falls and hits the ground. Okay? And we know there's a distance there. We are told it takes 1 second for this to fall. So the things that I want to know are my instantaneous velocity, right, when it hits the ground. That's one of the questions in the think question. I'm also asked what my average velocity or speed is when it's falling. And I want to know its distance above the ground. So let's do, okay, our instantaneous velocity first, right? Our equation for instantaneous velocity is g times t. So it's 10 meters per second squared times our time, which was just 1 second. So it's 10 meters per second, and it would be downward, right, to make it a vector quantity. Next, let's look at our average velocity or average speed. And remember, to do that, we're going to take our final speed and our initial speed, divide by 2. So we know that our final speed was 10 meters per second. Our initial speed was 0 meters per second because it wasn't moving, divided by 2. 10 plus 0 is 10 divided by 2 is 5 meters per second. And again, it still would have been downward. Lastly, it asks us to figure out our distance above the ground. So our distance is 1/2 gt squared. So 1/2 times 10 meters per second squared times our time, which was 1 second squared. So 1/2, or 1 squared is 1 times 10 is 10 divided by 2 is 5 meters. Now, there is another way you could do this. You also could figure out this distance by taking your average velocity and multiplying it by your time. And notice you get the same answer that way. You'd have your 5 meters per second on average times the 1 second, which still gives you 5 meters. So it doesn't really matter which way you do that, whichever way makes more sense to you. So that brings us to the end of section 6. The other sections here are pretty short. In section 4.7, it's talking about graphs of motion. We're not going to look at graphs a whole lot, but you do look at graphs quite a bit on your standardized tests, your SAT, that if you're a junior, you're going to take this spring. Okay, so we're going to take a look at our speed versus time graph, which is figure 4.11, and I should be able to, should be able to pull that up for you. So let me see here if I can get it. This one. We'll let it be this way and we'll write notes kind of on top of it. Okay. So some things to notice here. First off, our speed is on our y-axis, okay, which is our vertical axis. Our time is on our x-axis, which is our horizontal axis. This is a linear graph because the line is a straight line. And because it's a straight line, the slope of the line is constant, meaning it's unchanging. Hopefully in math at some point you've learned that your slope is your change in your y over your change in your x. Okay, this is also considered a direct proportion, which I spelled wrong, proportion. There we go. Which just means as one goes up, the other variable goes up. Or as one goes down, the other goes down. This is an upward one because our slope is positive. Okay. What's important about this is on this speed versus time graph, the slope represents acceleration. So this slope is actually the acceleration. Okay, so that's all we're going to kind of talk about this. We're not going to do a lot of graphing. Taking a look at, taking a look at the speed, or sorry, not speed, we already did that. The distance versus time. That's figure 412 in your notes. Again, I should be able to pull that up for us. Okay, again, notice that we have our distance is on our y-axis, time is on our x-axis. Because this is not a straight line, therefore it is non-linear, so it's not straight. This relationship in particular is quadratic. The curve is a parabolic or a parabola, and the slope changes. It's not constant. Okay, and that's really all we're going to talk about with this. Section 4.8 is really quick as well. It's about air resistance and falling objects. And again, remember earlier we talked about the fact that we were ignoring air resistance because it makes it more complicated, and we want to know that we want to make it simple. So again, you know from experience that a coin and a feather don't hit the floor at the same time when they're dropped at the same time. And that is because of air resistance. Right? That feather is more impacted by air resistance, and so it floats down more slowly than the coin does. However, in the absence of air resistance, so if there wasn't any air resistance, which you can get if you use a vacuum, and not like your vacuum cleaner, but like you have a tube and you pull all of the air out of it. Okay, the coin and feather would drop at the same rate because gravity acts on them the same. And again, that's what we do. When we do our calculations in this class, we are assuming there is no air resistance. We're ignoring it. So again, you kind of know from real life experience that air resistance noticeably slows the motion of an object with a large surface area, such as a feather, but is less noticeable on more compact objects, which is typically why when your textbook talks about something, it's going to talk about a coin falling or a rock falling because they are more compact. Okay, but again, we're always going to ignore air resistance. All right, just a little bit of clarification then about the differences, because most of these problems that you're going to be asked to do in physics are story problems. Okay. So kind of a little bit of clarification in this last section. It's very short about the differences between them. So most of your problems are story problems. Therefore, if you're asked to calculate how fast, you're being asked for speed or velocity, and you're going to use your V equals GT equation. If you're asked about how far, you're being asked about distance, and you're going to use your D equals 1/2 GT squared equation. Acceleration is not either of those. Acceleration is the rate at which velocity changes. So remember, you can have an acceleration if you have a change, an increase in speed, a decrease in speed, or a change in direction. Okay? Acceleration is a rate of a rate. And that wraps up Chapter 4. Have a great day. I'll talk to you tomorrow.